In this video, we are going to discuss on tutorial 22. So the topic is isothermal change and adiabatic change. Okay, question 1. After being compressed from 680 cm3 to 510 cm3, an ideal gas reached a final pressure of 162 kilopascal. So find the work done on the gas. So in this question, you are given initial velocity and final velocity, and not velocity, it's a volume, initial volume and final volume. And the volume is decreasing, so that's mean this is compressed. So that's mean the work done is on the gas, and you should get negative at final result. Okay, so final pressure is 162 kilopascal. Okay, so this is PF, we label as PF. So we're going to find work done. So we can use the formula work equals to PF VF ln VF over VI, final. So we use formula with ln because pressure, volume change, okay, and pressure also change, okay, final pressure difference. So we substitute the formula. We substitute the pressure 162 kilopascal, so convert to pascal. V final 510 times 10 to the power of negative 6, convert to meter cube. Okay, volume 510 and 680 centimeter cube. So no need to convert to meter because you get the same answer. This involve ratio. So we got same answer. Okay, now the answer is negative 23.8 joule. So we get negative. Why? Because this is work done on the gas. Okay, next we go to question 2. The graph shows 2 moles of an ideal gas which undergoes an isothermal constant temperature change XY followed by an isobaric constant pressure. The change is Y to Z. Okay, so we have two processes here, isothermal and isobaric. Okay, we can read from the graph each value, pressure and volume at Y, at X, Y, and Z. So we are going to find the work done by the gas. So the work done by the gas from the graph PV graph, we can calculate using area under the graph, area under the graph, or using the formula. Okay, so the work done by the gas will be the total of work done in isothermal and in isobaric. So for isothermal process, we need n number of moles. So given here number of moles 2, and for isothermal process, and plus the work done for isobaric process. Okay, for isothermal first. For isothermal, x to y, so x to y is we use because this is isothermal, so we use the formula with ln. Okay, so work xy equals to PV ln VF over VI. So PV is also equals to nRT. So we can substitute the n number of moles, R 8.31, and temperature not given, okay, but we can find the temperature because temperature is constant. So that's mean temperature at X equals to temperature at Y. So temperature we can use PV equals to nRT also for at X. PX VX equals to nRTX. Also we can use PY VY equals to nRTY because the temperature for isothermal is constant, constant temperature. So let's say we choose this one, PX VX equals to nRTX. So TX is equals to PX VX over nR. So we substitute the pressure, the pressure here 1.5, 1.5 times 10 to the power of 5. So here this P is typing error, so we substitute Px, we substitute the Vx, 6 times 10 to the power of negative 2 divided by 2, and then R 8.31. So the temperature at X is 541.5 Kelvin. So the temperature at X equals to the temperature at Y. Okay, now we substitute into the equation here to find work. So N number of moles are 8.31, temperature 541.5 ln. The volume, the final volume is 9 times 10 to the power of negative 2, and the initial volume is the initial volume, okay, this one is the work done x to y. The initial volume is 6 times 10 to the power of negative 2. Okay, then we get work 3649.08 joule. So lastly only then we round off to the correct number of significant figures. So we calculate the work done y to z first. So the work done is area under the graph. So P times the change in volume. So the P will be 1 times 10 to the power of 5 Pascal. Okay, and then the Vz 12 minus 9, okay, times 10 to the power of negative 2 meter cube. So the answer is 3000 joule. Okay, then we add these two. Total of work done will be 6649.08 joule. So we write we convert it to two significant figures also can so 6,600 joule. Okay, 6,600 joule, or three significant figures 6650 6650 joule. Okay, don't write too many number of significant figures. So 2 or 3 is still allowed. 3 significant figures still allowed. Okay, so now we go to question 3. Okay, question 3. 1 mole of an ideal gas expands adiabatically from initial pressure 90 kilopascal and initial temperature 310 Kelvin to final pressure 82 kilopascal and final temperature 299 Kelvin. So determine if the gas is monoatomic, diatomic, or polyatomic. Then find the work done by the gas. So we are given is adiabatic change. The process is adiabatic change. So expand, so that means the work done will be positive, and pressure initial 90 kilopascal, final pressure initial temperature 300 Kelvin, final pressure, and final temperature. So all this is given. So to determine if the gas is monoatomic, diatomic, or polyatomic, so we need to find the gamma ratio of CPM to CVM. Okay, the gamma. And then okay, because this is adiabatic, so you can find gamma using the three equation here. Choose the one that given the information we can get from the okay, question here. Okay, so volume don't have, so that's mean we use the last equation here. So P1 to the power 1 minus gamma, T1 to the power of gamma equals to P2 to the power 1 minus gamma, and T2 to the power of gamma. So we can calculate gamma to determine whether the gas is monoatomic, diatomic, or polyatomic. Okay, so from here we substitute the P and T given. Okay, so we rearrange here the equation. So we substitute PI and PF, and then to find the gamma, so the power here we multiply both sides by 1 over gamma. Okay, so on the right side, gamma times 1 over gamma, we cancel out, become to the power of 1. Right side will be 1 over gamma minus 1. So 1 times 1 over gamma, and then gamma times 1 over gamma is 1. Okay, so now we can solve using log rule. Okay, log rule. Okay, so here we substitute the P and T given, final and initial. Okay, take log both sides. Okay, take log both sides, then bring together the log here, and we solve, we get negative 0.3881. Okay, so the gamma will be 1.63. Okay, so you bring 1 to the right side, plus 1, and 1 over gamma here, so you get gamma 1.63. So for 1.63, we know this means that the type of gas is the monoatomic. Okay, so it's a monoatomic gas. Okay, next we go to question B. Find the work done by the gas. So the work done by the gas, we use the formula for adiabatic work. Okay, adiabatic work, the formula is okay, these two. So we choose the one that we know. So volume not given. So we choose the temperature, the second equation. Work equals to NR over gamma minus 1 bracket T1 minus T2. So we have already derived this formula from our lesson. So we just take the formula directly and we substitute. And 1 mole. So number of mole is 1. They're given here 1. Okay, R 8.31, temperature is initial minus final, 310 minus 299. Okay, gamma is 1.63 minus 1. So the answer is 145.10 joule. So you round this off to 3 significant figures. Okay, so you get 145 joule. Okay, don't write in too many number of significant figures like this one. Okay, so now we go to question 4. 3 moles of an ideal gas is at a pressure of 1.62 times 10 to the power 5 Pascal and a volume of 0.0650 meter cube. So the gas is then compressed adiabatically to 1 over 4 of the initial volume. So calculate the work done on the gas and what is the change in internal energy of the gas given that gamma equals to 1.33. So for gamma 1.33, the gas is polyatomic. Polyatomic. Okay, so N is 3, pressure, initial pressure, then the volume, initial volume. So compressed adiabatically, so this is compression, so the work done will be negative. Okay, then is a adiabatic change or process. Final volume is 1 over 4 of the initial. Okay, so now from the adiabatic work formula, okay, so there are two formula here. We choose the top one this time because volume is given, temperature not given, so we choose the top equation. Okay, so for the okay, for the volume given, temperature not given. So for the PV here, we use the first equation, P I V I to the power of gamma equals to P not V not to the power of gamma, or final P final V final to the power of gamma. Okay, so this one is to find volume or pressure, final pressure. Okay, so this is the formula we are going to use. Okay, for pressure, final pressure, we use this equation. Okay, so we substitute the value. Okay, so initial pressure there 1.62 times 10 to the 5. Final volume 1 over 4 times 0. This is final okay, the final first and then divided by initial. So you make this opposite. V final will be this one, 1 over 4 times 0.0650. Okay, so you get the answer 1.02 times 10 to the 6 Pascal. Okay, so you make this correction. Okay, for VF first, then divided by VI. Okay, let's check PF, PI, VI, PI, VI. Okay, correct. VI first. So from here, there's a typing mistake here. So PF is PI, VI to the power of gamma. So VI on top. Okay, VI on top. So this one is correct. Okay, this one is correct. So the label here wrong. So the answer, that means the answer is correct. Okay, then you substitute into the equation the P final just now. Okay, this is VF, PI, VI. Then gamma 1.33 given here, minus 1. The answer is work done negative 1.83 times 10 to the 4 joule. So we get negative because the work done is on the gas. So it's a negative work. So correct. Now question B, to find the change in internal energy. So to find the change in internal energy, so we use first law of thermodynamics. So delta Q equals to work plus delta U. Okay, delta Q is 0 for adiabatic. So this is special characteristic for adiabatic process. So delta Q is equals to 0. No heat is allowed to enter or to leave the system for adiabatic change. Okay, so that's mean work is equals to the internal energy. So we calculated already work in A. So we just substitute into the equation. So don't forget to substitute together with the negative because you get internal energy increases. So you get positive. Positive 1.83 times 10 to the power 4 joules. So that's mean the internal energy increases. Okay, the internal energy increases. Okay, now we go to the question 5. Okay, so the graph given here, the state start from W. Okay, W, X, Y to Z. So the change in the state is from W, X, Y, Z and then back to W. So this is a cyclic process because it goes back to the initial situation. So W here. So we are going to fill in the graph here. Okay, given change in internal energy, negative 8T. So to find the change in heat and the work done, so you can use the first law of thermodynamics. Okay. So for the what W to X is area, work is area under the graph. Okay, so this is the PV graph. So you can calculate the work done, area under the graph. So you substitute 160 kilopascal, convert to pascal, and then the change in volume is 10 minus 4. So times 10 to the power of negative 4. So we get work done, negative 96. So negative 96, we substitute into the first law of thermodynamics to get delta Q. So you get negative 176 joule. Okay, next X to Y. X to Y is a constant volume. So that's mean the work done is automatically 0 because constant volume. Okay, so the work done is 0. Then for the change in heat, we use first law of thermodynamics. Okay, we substitute work 0 here plus the internal energy given 60. So you get delta Q 60, positive. Okay, change in heat is positive 60. Okay, next we go to question C. This time you are given change in heat. So Y to Z. So Y to Z, the change in heat, the 180. Okay, so from the first law of thermodynamics, we need to calculate the work done to get heat, to get internal energy. Okay, so we can calculate area under the graph. So it's the 280 times 10 to the power of 3 kilopascal convert to pascal. And then the change of volume is 10 minus 4 times 10 to the power of negative 4. So you get the work done 168. Okay, you substitute, you put here in the table. And the change in internal energy, we use first law of thermodynamics. And you get internal change in internal energy 12 joule. Okay, so all positive. Okay, so next, lastly, Z to W. So again here, Z to W is constant volume. No changes in volume. So that's mean the work done is 0. So the work done is 0. Okay, next is to find internal energy. So internal energy is the same as the X to Y. Okay, X to Y. So will be negative 60 because temperature decreases. Z to W, temperature decreases. So that's mean the internal energy also decreases. So it's negative 60. And the change in heat, we substitute into the first law of thermodynamics and we also get negative 60 joule. So it's opposite from the process of XY. Okay, because it's down. And the arrow didn't put here. I forgot to put the arrow. So the arrow, but in the question given already, W to X, X to Y, Y to Z, and Z to W. Okay, so you can complete the diagram here, graph here, by drawing the arrow. Okay, so now we go to last question 6. The graph shows a fixed mass of ideal gas undergoing adiabatic compression from A to B and isothermal expansion from B to C. Okay, so this is not a cyclic process because the process doesn't go back to its initial state. So A to B, B to C. A to B is adiabatic, B to C is isothermal process. Okay, then look at the arrow. Adiabatic is compression, work is negative, whereas BC is expansion, so the work is positive. Okay, so the change in work, heat, internal energy, and internal energy for the process A to B first. So this is adiabatic. So the change in internal energy and change in heat, and then the work done. Okay. So internal energy, so the TB is larger than TA. Okay, so you can imagine the another BC is isotherm. So there you can imagine the another isotherm down here. So that's mean temperature at A is less than B, less than at B. So temperature and the temperature at B is higher than temperature at A. Okay, so if temperature increases, here look at the arrow. If temperature increases, that's mean internal energy we get positive. Okay, so adiabatic process, the special characteristic is no heat is allowed to enter or leave the system. So that's mean delta Q is 0. Okay, and lastly, the work done, we can use first law of thermodynamic. So if delta Q 0, so the work done will be equals to the negative delta U. So delta U we get positive, so that's mean internal energy work done we will get negative. Negative. And it's logic because this is compression. So we got work should be negative delta U. So the work done on the gas. Okay, now we go to B to C. Okay, so we go B to C. B to C is isothermal. So for isothermal expansion, okay, the characteristic for isothermal expansion is constant temperature. So if constant temperature, so there is no change in internal energy. So the change in internal energy will be 0. Okay, so next we are going to do the change in delta Q and work done. Okay, so for change in internal energy, we get 0. For delta Q, we can use first law of thermodynamic, work plus delta U. So if delta U 0, so the work is equals to the delta Q. So the work done is positive because look at the arrow, this is expansion. So if the work positive, so that's mean delta Q also positive. So that's mean the heat is absorbed by the system. Okay, so delta Q equals to work, and the work we can find here also positive because this is expansion. So the work done by the gas and the work is positive. Okay, so that's all for question 6. That's the answer. Okay, now it's the end of tutorial 22. So bye bye.